Cool. Welcome to the online people. This has been a headache to set up, but here we are. Yes. A stochastic matrix. Yeah. Big picture. What is a stochastic? What sort of questions would you be asked, or like a specific type of thing? Yeah. Cool. So to start, what a stochastic matrix is it's something that's very applicable to people that study things like steady states or like for those of you who are mechanical and aerospace engineers, this is how people usually look at like vibrational stuff, how things sort of level out over time. What a steady state is, what a stochastic matrix is it is, by definition, a matrix that describes probabilities of transition, okay? What I mean by that is if I have three different places, place A, place B, and place C, okay? And after one instance of time or one change, one something like that. So let's say we have three cafes, Cafe A, Cafe B, and Cafe C, okay? On a given day, we have 200 people that each go and buy coffee, okay? For the people that bought Cafe A, they found that there's a 70% chance that they stay there, okay? If they bought the Cafe A the previous day, there's a 20% chance that they'll go to B the next day, and a 10% chance they'll go to C on the next, okay? This kind of makes sense so far? Just kind of like, hey, given this, where do they go the following day? Okay. Starting at Cafe B, there's only a 20% chance that they'll stay there. There's a 50% chance that they'll go back to A. And what percent chance does that leave us going to C? We have 20% staying and 50% going to A. How much is left? 30, right? This is the idea of why a stochastic matrix has to sum to 100%. And I'll go over how to draw this as stochastic in a moment. But all this is saying is these little arrows are describing my total population and where they're going, okay? And of course, you have to have 100% of your population, okay? Lastly, for C, we'll once again have 70% going here, and we'll have 30% going here, and we'll have 0% going here, okay? We'll move this down because of that stupid whiteboard thing. All right, cool. So if I wanted to write this as a stochastic matrix, if I wanted to represent this in something that makes a little bit more sense to look at than a bunch of circles and arrows, okay? How I do that is, well, we're in linear algebra, so we're probably going to draw a matrix. And I always write it exactly the same, start and end, okay? I'll just move these away just a little. All right. So this is going to be my stochastic matrix, okay? And I draw a little line here just because I'm an electrical engineer, and that's kind of something you do for stuff like this. Separate it, keep your mind separate. Bless you. I'm going to draw my three things. I'm going to draw A, I'm going to draw B, I'm going to draw C. And then over here, I'm going to draw A, I'm going to draw B, I'm going to draw C. Okay. Okay. So looking at this and tying these sort of things together, what percent of people start in A and end in A? 70%, right? 0.7. How many start in A and end in B? 0.1. And how many start in A and end in C? 20%. Okay. Following with B, how many people start? Yeah. B is 20. 8. Oh, I wrote that backwards. You're so right. Thank you. 2. I just can't read, but that's why I have 2 degrees in engineering. So now let's look at the second column. What about starting in B and ending in B? This is where a lot of students get a little confused because you have to pay attention to where you're lining up. Okay, you need to be in the middle position, not the top. The top one was starting in A and ending in A for the last column. So here, starting in B and ending in B is 0.2 once more. Starting in B and ending in A is 0.5%. And without even looking, I can tell that this one has to be 30%. Okay. Filling in the last column, starting in C and ending in A is a 0.3. Why did you stop charging? Come on, stupid shit. Okay. Why do people leave markers in rooms like this? This is absurd. I don't mean to be bitter today. I am a little bit. Okay. starting in C and ending in B. Starting in C, ending in B, 0. Okay, starting in C, ending in C, 70%. This is how you fill in a stochastic matrix. Okay, does it make sense up to this point how to just construct it based on something like a word problem? Like usually they like to do the fantasy classes one. I think they did that in the worksheet. It's like starting an archer and ending as a barbarian. Starting an archer, working as a cleric. Somehow miraculously, they always start with A, B, and C for nothing but convenience. Another thing to note is it doesn't matter which order you put these in as long as you keep them consistent. This could be BAC or BCA as long as this is the exact same. You just need to make sure you keep that consistent. It should be easy enough to label them A, B, and C, A, B, and C though, right? Or 1, 2, 3, 1, 2, 3, depending on how you define it. You just want to make sure that this looks the same as this. Okay? Yep, come on. We're not charging again. Why are we not charging? Why would such an expensive tool not work? Okay. Oh, it stopped screen share. I am all over the place. Come on. Okay, so some facts about stochastic matrices. Okay, stochastic matrices are usually taught immediately after eigenvalues, just because a stochastic matrix has a few very interesting things about it that have to do with eigenvalues. In particular, they always have an eigenvalue of 1, and the dimension of that eigenspace is one-dimensional as well. Okay, what that means. What that means is when I'm looking at this and I can try to find like an eigenspace, I know I have a lambda of 1, and I know when I solve for that eigenspace, it'll be a line, a one-dimensional thing. Okay. So, how many of you have taken calculus before? In some form or another, somewhere. Do y'all remember doing stuff like you had a nice little graph and you had to draw the derivative at all these different points? Y'all remember these? Some degree. This is what you're actually doing for a stochastic matrix. What you're doing is you're dropping a starting point here, and we approach a steady state, a place that is flatlined for however long. Okay. You'll study this to be able to say differential equations. This is something that pops up a lot, studying with matrices and derivatives and all the fun stuff that goes with it. But the premise is, knowing we have a stochastic matrix that looks like this, we can find wherever that line is, wherever we're approaching, okay? So to do that, we always do the null space of A minus 1 times I. Always, always, always. This will always get you your one eigenspace, and it will always be one-dimensional, okay? So this is something you should know how to do at this point, but just as a step back, kind of review it. Okay, you will start with a matrix A minus, in this case, 1I. When in doubt, if you have a matrix in this class, what do? Row reduce. Put it in reduced row echelon form. From here, and put it in parametric vector form, and from there, your vector is equal to your eigenvector, okay? So your one eigenvector. Okay. So this is how you would find something like an eigenspace for this. This is how you would solve one of these problems, okay? And for the sake of this question, let's say you get something that looks like 0.4, 0.8, and 1.2, okay? What do we not like about this vector? And why do we want it to end up with summing up to 100%? Yeah, they're percentages, right? We're still talking about percentages, but you can, this is, what these are proportions, but we want a proportion that sums to 100%, okay? These are still relative to each other, but we want it to make the most sense. Bless you. So the next thing we do is we divide by the sum here. And what we have is we have divided by 2.4. Okay, so we're just dividing by the sum of all of these entries to get us a nice, pretty vector that sums to 100%. Okay, so let's say in this case, this gives us the vector, this would be, oh God, what's that? 1/6? Yeah. 1/6, 1/3, and 1/2. Okay. So as time goes to infinity, what a steady state is that all of the people I have that start in A and B and C according to this, again, this isn't me actually calculating, this is just me, not slaving over it, and I know y'all don't want to watch me row reduce, you know how to do that. What will happen according to this is the total number of people I start with, a sixth of them will be in A, a third of them will be in B, and half of them will be in C, okay? And what happens when we have them in those proportions in these three spaces, okay? We have the sixth, a third, and half. If I do another instance and move everything along these lines, we'll end up with the exact same thing. Nothing will change. It's the idea of what a steady state is. We're at a place where doing another thing does nothing. That's the one eigenspace. Motherfucker. Now I'm going to go and turn low power mode off. Yes, I know the meeting is being recorded. Battery off. One. Oh, come on. There we go. All right. So does everything so far make sense? Do we have any questions on anything I've talked about for stochastic matrices? Okay. This is not your steady state vector because this only describes the proportions, not how many people end up in places. So a way word problem would phrase this would be on day one, say we have 20 people going to cafe A, we have 80 people going to cafe B, and we have 140 people going to cafe C. Okay. What happens as time goes to infinity? How many people are shopping in each of these cafes? Well, using what we know about something like this, does it matter where we start? No, we'll always approach that steady state. That's why it's called that. Okay, no matter where we begin, we will always end in the same place, and that is our steady state vector. So we don't care what this is. We only care how many people we start with. Okay, so we add these up to get the total number of people, which would be 240 customers. Okay, so now we know we start with 240 people, and we end up with the proportions of where they are. So how do we find out how many people are going to be at each of those places? Yeah, you just multiply them, right? Proportion times total just gives you the amount in each. So we just multiply 240 times 1/6, 1/3, 1/2. And this gives us as a to the infinity of n, a to the infinity times some random vector x will give us 1/6 of 240 is 40, I think. 1/3 of it, I think, is 80. This should be 120. Yeah, there you go. This is exactly how you would solve a problem like this. This is about as intense of a question they could ask about stochastic matrices. Okay.
This is the steady state vector, right?
Yes, this is what you would call the steady state vector. These are where we approach as time goes to infinity. Okay. This is on your last midterm. Well, I know that actually. I graded the problem. But stochastic matrices. Does it make sense why something like this would be applicable in like a business perspective for someone who's looking at like how things are changing, how stuff like that happens? Like this is something that is actually incredibly relevant for stuff like that. In particular, Google actually uses stochastic matrices to decide how it suggests certain pages to you. Called Google Matrix. There's some kind of dampening stuff and other little additional things. But this is how websites kind of decide what you should be seeing. Okay. Cool stuff. You know how to do it, right? Any other questions on stochastic matrix? Does that kind of cover everything? Do you have any other questions on that? Okay, pretty straightforward process, right? You want to sum it all up, find the one eigenspace, normalize it, multiply by your start. Cool. Yeah.
It's not a positive stochastic matrix. We know that there's a one eigenspace, but we also have to solve for the other eigenspace.
If it is not a positive stochastic matrix, you will not see it. It's just a matrix.
Well, if it's a stochastic matrix, a non-positive stochastic matrix. Well, I guess
For the sake of this class, you will not see negative percentages.
okay.
For the sake of this class.
Oh,
That should be expected. Yeah, I've never even heard of that ever popping up. Did y'all talk about that in lecture at all? Did? Okay, that was more of just a mention than conversation. But I'm a little wary saying that because I've also told my students before, no, they won't give you a 4x4 matrix and ask you to find eigenvalues and eigenvectors. That would be despicable. And then they did. So this is what this is. This is a stochastic matrix. I have never seen on the homework on anything else, anything relating to a non-positive stochastic matrix.
Okay.
Cool. Cool. Other questions?
Question 35 is study Palooza. I have it pulled up.
Question 35 from the study Palooza. We absolutely. Yes, we can. Can I see it?
Then you can turn the brightness up.
No, this is good. All right. So I'm just going to write this problem out on here. This is 3u minus 8v dotted with 4u. Okay. And it's given that u and v are orthogonal and both have magnitude 1. So magnitude u equals magnitude v equals 1. And u dotted with v is equal to 0. So let's talk about all of the things going on here first. Okay. You guys have seen like magnitudes of stuff before, right? It's a Euclidean distance is what it's called. Distance in space, straight. Okay. There's some other non-Euclidean distances, which are things like a sphere, like the Earth. You have non-Euclidean distance because you have to go around a curve, but this is all straight lines. Okay. So this is just saying they have a length of 1. Okay. What is a dot product? For those of you who are in my studio, I would not like you to answer, but those of you who haven't heard me talk about a dot product, what is a dot product? Without having to tell me about a number, what is a dot product in essence? Yeah.
Projection onto the other.
Almost. Now, that's not the full extent of what it is, but it can help you get there, right? It can help you get to a projection. But what is a dot product? It's like high level. What is it? What does it tell you?
It's helpful to that way.
It would be that's how you compute it. But what does it describe? Like we have like determinants which determine invertibility, right? That's a characterization of them. What do dot products do? Well, a dot product is it's simple to compute, right? Just multiplying two things together. But what it is it's a measure of how parallel something is. Okay? So if you dot two things together and they are 0 amount parallel, what would you call them? Orthogonal, exactly. That's what a dot product is. It's telling you, hey, these two things don't point in the same direction at all. Okay? That's why it comes up in things like projections, because you take the amount of parallel that it is, and that helps you get to what a projection is. Okay? So another thing about dot products is, what is the first word in the name of this class?
Linear.
Linear. Okay, what are the 3 things that make something linear? You know them. I know all of you know them.
You can multiply by a constant.
You can multiply by a constant.
There, you can distribute, or like.
That's multiplying by a constant.
No, not distributing a constant, but like if you multiply by another variable, like, it's commutative.
It's commutative, so we can add, right?
Yeah.
Yes. So closed under addition, closed under multiplication allow you to distribute. What is the third characterization? You know it. It's the same thing as subspaces. And what is the third thing for subspaces?
And
Must contain 0. That's the definition of linearity, actually. That's why we talk about subspaces. Those rules define what something is to be linear. Okay. In this class, we're talking about something that's linear. So how do you think we can break this up? Do you think we can just distribute this? It's a linear operator. You can think of it as just distributing. So we can change it from here to be 3u dotted with 4u minus 8v dotted with 4u. Okay. And this then gives me 12u dotted with u, put parentheses around that, minus, well, it's 32, but v dotted with u. And what did we say v dotted with u is? 0. They don't point in the same direction. This goes away. Okay. What is u dotted with u? How much is something pointing in the same direction as itself? 100%. So if they have a distance of 1, their dot product is still 1. Okay. It's technically also the dot product of itself is its magnitude squared. Okay. But if it's only has a magnitude of 1, it's still 1 after we square it. So this just yields 12. that make sense? That's the answer, right? Yeah.
When it says orthogonal, like that means that it's gonna be zero, u times v is zero?
U dot. U dot v is 0.
Okay,
Because if they're orthogonal, they have a 90-degree angle between them. They're pointing in opposite directions, and they're in no amount parallel. They're not parallel, they're orthogonal. Okay, cool.
so for, it's just like, that.
Yeah, solve it.
Okay.
Yeah, solve for what this is numerically. When you get this, and then you get in the next pretty 12. Cool.
What were the numbers?
They're not going to be numbers that you like need a calculator for, but sometimes it's like, hey, find the magnitude of this vector, and the vector is like 3, 1, 4. Okay, find the magnitude of this. Just the square root of 9 plus 1 plus 16, right? Which is going to be the square root of 26, which you can simplify that. You're not gonna tell me that it's 5.092, whatever the fuck it is. But this isn't unreasonable, right? You can't simplify that any, I don't think. So that's your answer. You can just leave it as something like that. Sometimes you'll get weird fractions. 7/13 isn't a horrible answer. It's not impossible, but don't be afraid of it. Okay, they're not going to be like, you're not going to have to find like the common denominator between 4-digit numbers. No, we don't want to grade that. Like, not only do y'all not want to do it, we don't want to grade it. So let's try to. I don't write the exams. They will try to make it as easy as. Great. Other questions? Yeah.
You explain like the difference between like a projection matrix
Mhm.
versus like the squares.
Yes. So total preference. I'll go through them just so we can talk about what they are. But there's some tips and tricks in how to do things quickly. And there are the ways that will never fail you, that will always be correct. It's just kind of a use case for everything. All right. So one of the most common ways you'll see this is to find the projection of a vector onto a line. Okay, very simple formula. All right. So let's draw out, first of all, what a projection is. So I have some line that I'll call W, and I have some vector I'll call Y. Okay. What a projection is if like my arm is this line, okay? What a projection is that basically if I have two things on the other side, just smashing everything down, right? You can also think of it as one giant flashlight. So if we're looking at this, I can put a giant flashlight here and shine down, and whatever my shadow is of that line, okay? That's my projection, all right? So let's draw that out. Here's my giant flashlight shining down, and we're gonna get a shadow that looks like this. Y, W, and there's my projection, okay? The difference between them is called the orthogonal projection, Y, W, perfect. Okay. This is what it looks like. So there is an easy formula for how to project these things, but I'll go through just how we get to that formula first. So how else can we define W? We can't just define a line as a line. How do we define lines in this class?
Subspace.
We define them as a subspace. How do we define what a subspace points in? As a span with what? Yeah, just a vector, right? We just need a vector that points on that line, and it creates a span and a subspace, and blah, blah, blah. Okay. So to always define this, we just call it the span of some vector U. U is totally arbitrary. Okay. You can pick any vector on here. Okay. If you can count like the little coordinates and just find the vector, that's fine. It's a great place to start. Bless you. Okay. So let's say for this one, I take this value of U. Okay. Totally arbitrary, just has to be on here. We're trying to solve for this blue one, so we don't know what it is yet. Okay. So how do you think we start looking for how the projection? We've talked about it before. We're going to start with a dot product. Okay. To find the projection, we're going to start with Y dotted with U. Okay. It's a measure of how much we're pointing in the same direction. Okay. But U is arbitrary, right? We can pick any U, and this will give us different results because there'll be different numbers in U. So how can we kind of make sure that doesn't quite happen? What's something we can do? What? We can divide by u to just make it a standard length, right? So we divide by the magnitude of u. Okay. So now we have u over the magnitude, so it'll always be exactly the same length. Whatever we started as, it'll get shrunk down to be whatever that length is, okay? And it actually works out that the signs cancel out if you pick them pointing in the opposite direction. It'll always be exactly the same. Okay. Now, is this a number or a vector?
Number.
It's a number, right? It's not what we want. We want a vector. We want YW. We want this. Which direction do we want it pointing in? The direction of Y or the direction of U? U, right? We want it to be on W, right? We want it to be the part of Y, but we want it to point in the direction of this line, right? So we're going to multiply by U again, but this time it's just the vector itself. Okay, we have to do the same thing. We have to normalize it. So we once again divide by the magnitude of U. We get this lovely equation. It's probably familiar to you. You've probably seen it in slides or stuff like that. So this is the easiest way to find YW. Assuming that you're finding something as simple as the projection of a line onto of a vector onto a line. Easy, done, bam, cool, right? Nothing impossible. Little square root, little dot products, multiplying that out. Okay, so far so good. This is the only like easy, quick, bam, way done. Okay, for specific instance, you'll probably be asked this. They love asking. To find generalized matrices that we define as like some matrix B times X gives me the projection of X onto W. Okay, to find this matrix B, there are three main ways that we can do it. One of them is only applicable for projecting onto a line. The other two are generally always applicable. Okay, first way, and this is only for a line. Okay, it's pretty much the same equation. It is U times U transpose divided by the magnitude of U squared. This will yield you an n by n matrix that is exactly what describes your matrix B. Right? Number two and number three are actually a bit of a headache, but not impossible. Number two is something that you've been doing for a bit now, is to find B equals a C inverse D composition. Okay, to do that, first of all, what are the eigenvalues of a projection? 0 and 1, so you can figure out what your diagonal matrix is, right? One's everywhere, a single 0 on the diagonal. Okay. To find the basis of your W, that'll be the vectors it provides as a basis for W, right? This is projected onto a plane by these two vectors. Boom, that's your one eigenspace. Cool? Right, so good? Yeah.
Do you always have 1, 0 vector, or do you have multiple?
You will always have one.
Only one?
But you'll have however many is. So if we're projecting onto a line into space, right? How big is our line? How many dimensions? The line itself is one dimension, right? So, but what space is it in? So how many dimensions does the orthogonal space have to be?
It has to be 1.
You have to add to 2, right? W and W per have to add to n. Okay. If I'm in 6D, and my space W is 4-dimensional. How big is W per? 2-dimensional, right? If I'm in 18D and I have a 9-dimensional W, how big is W per? 9. They're hard words that just mean subtract. Okay. Yeah.
For U, that's still using the same example as the
Exactly. Some vector on that line. Or yeah, some vector that creates a basis of that line. Yep.
And then how many times is the lambda equals 1?
However big W is, right?
Oh, so
So W is your one
W is 1
eigenspace.
and the 0 is lambda per.
Yeah, all this orthogonal junk just means one eigenspace and 0 eigenspace. That's all you're really finding. Okay. But it's a little complicated. In particular, you're going to find a basis for W, which is your one eigenspace. Okay, and to do this, it's just the columns of A, where we say like A is like V1, V2, you know, whatever vectors it provides that form a basis for W, okay? W perp, a little bit more complicated. This is your 0 eigenspace. Not of A, but of the projection matrix B. So we don't actually have the full matrix and we can't just find the null space. what we have to do is if this is equal to W, okay, then W perp is equal to the columns of A perp. And if this is true, this has to be equal to the null of A transpose. Okay, because there's a set of formulas that all tie this sort of stuff together that I'll write out. Okay, this is where this equation comes from. Okay, you'll see this in 4 different forms in like your textbook and what you discuss in the slides and stuff. I like to write it like this because 1, I like the nice little color, and 2, I think it's more intuitive. Okay, what this equation states: one of these red boxes must be a transpose, and one of the blue boxes must be an orthogonal. Okay. So, for example, if I'm finding the column space of A transpose perp, it is the null space of A empty empty. Cool? Does that make sense? If I'm finding the column space of A transpose, that's going to be equal to what? The null space of A perp, right? Because over here we filled the red box, so this can't be filled. But the blue box is empty, so it has to be full over here. Okay, this is how we have a set of 4 equations that I just like to smash into 1. Okay. So again, to reiterate that, if they say to find the null space of A transpose, okay, that means my red box is filled over here, right? So I have to be able to make it column space of A. Right. Does that make sense? Cool. Okay. So that is how you would fill a matrix B with that CBC inverse. Because this gives you your basis for a 1 eigenspace and a 0 eigenspace. Okay. So you find the basis of null A transpose with parametric vector form, you get your vectors, boom, you're done. Well, then you multiply out 3 matrices, which is a headache, not impossible, just a headache. Okay. The last way to find a generalized matrix, B is equal to A transpose, inverse, A transpose. Okay, where A is, once again, you're like B1, B2, B3, whatever, however big W is, that makes your columns A. That makes sense? This sucks, multiplying out 4 matrices and finding an inverse. Not impossible, right? But these are the general ways to find those projection matrices. Okay, yeah,
Are they gonna ask us to do a specific way? Have you seen in the past? that-
I've never seen them ask a specific way. One other thing to note here, is if you plug in just U for A, you'll get that first formula. So the shortcut for the line, it's just this equation. Okay. Okay. So one other thing I want to talk about is least squares. Okay. Least squares ties into this sort of stuff very well. It is my preferred method to find a projection in general, actually. Okay. It is always exactly the same process. Okay. So I'm just going to draw a line and write least squares. Okay. How many of you have taken a class like AP Stats? Some sort of statistical equivalent at some level of education. Stats class? Yeah. How many of you have done curve fitting to some extent at any point? No? Okay. Not many, but that's fine. Least squares is usually how we fit curves in general. Okay. If you have a bunch of data points, you want to fit some kind of smooth something to it, whether it's a quadratic, whether it's some kind of weird sine function. You can always use a least squares to get you there with some little asterisk there, but that's not the point. In MATLAB, for those of you who are using the tool, this is exactly how it does a polynomial fit. This is what it is. You don't have to use a polynomial fit if you want to use least squares. It's the same thing. Okay. What it is we start with a matrix A, and then we start with some Y. Okay. And our goal can be 2 different things. Okay. 1, curve fit. Okay. Goal number 2 is find the Y, W. Okay. If they say least squares, they mean this. First point. Okay. For what I'm talking about, I'm going to go 1. You will always do at least up to 1. If you do the second part, you'll get the projection as well. Okay. For something where it's asking like, hey, given these 4 different X and Y coordinates, find a line. That's goal one. We're curve fitting. Okay, we're not finding projections. We're curve fitting. Process is always exactly the same. You have some arbitrary x that we don't know, right? Doesn't matter. We're solving for solutions anyway. Okay. To do this, the process is always identical. A transpose A augmented with A transpose Y. By some theorem, which I can't remember the name of, you will always solve it to be the identity augmented with some vector on the right-hand side. Okay. What this vector is this describes the input to get you closest to the output. Okay. The input that describes how you get closest, that's curve fitting, right? How you get that curve as close to everything, that's a curve, right? That makes sense. Okay, so this is where you stop. For goal one, which is actual least squares. Okay. But if we want to take it a step further, we can multiply A by the input that gets us closest to our output. Okay. And if we multiply by the input that gets us closest to the output, we're going to get the closest thing to y in W. And what is the closest thing to y in a space W?
YW?
YW, the projection, right? The projection is by definition the closest you can get. Okay. Because if we want to look back up here, okay, what we have is you can think of this as like try to get as close as you can, and you find that the closest point is at exactly a right angle to that line. That's how we get our YW, right? And this will always yield our YW. Boom. And this would be goal two. Okay, to find a projection. This does not give you a general matrix that describes a projection. This is a use case for finding a single projection. Make sense? They say find the general matrix to describe the projection. They are not talking about this. They are talking about doing one of the formulas we've talked about before. Okay. Does that make sense? Yeah.
Yeah, sorry, for the
No, you're good.
projection matrix, for the formula on the textbook, that's the transpose.
Oh, God damn it. Yeah, that's my bad. I apologize. I always
Or
get that.
that's like the first transpose is right, but the one inside.
Oh, yeah, you're right. You're right. So this is transpose.
Yeah, and then the first A.
This is transpose. Okay. Cool. Sorry, I do always get that one a little backwards. As myself, it's hard enough to remember, right? This isn't something you'll see very often.
So we can just use like the least squares
Always,
instead of doing.
always. If you're only looking for projection, not if you're looking for the general matrix to describe a projection. That makes sense. In general, like I'm a PhD student. I do curve fitting all the time. I do all kinds of stuff where I'm trying to get the closest template, trying to get the closest whatever. This is it. This is how people actually manage data like that. Least squares process. Wonderful. Okay. Yeah.
The only difference between 3 and the other ones that find the matrix full of weights.
So 3 and 2 both generally always find the matrix for projection. For 1, it also finds the matrix of projection, but the only case is when it's aligned. Okay, that's the only case we can use number 1. All right. So going back down here, we can get a projection. Least squares. Never impossible. Just maybe a bit of a headache because we're multiplying matrices together. Right. Yeah.
So historically on finals, do you typically use like method 4 and 1, or has there ever been a scenario where you have to do like the big pain in the ass formula?
I have not, I can't remember, but I wouldn't worry about it too much. I would just kind of remember it, look at it, and then once you get your exam, once they say begin, open the first page, write the formula down. Just have it quick short-term memory so you have the formula. Because it's not as interesting for us to watch you plug in numbers, right? That's not the point of learning. Well, apparently a hot take, but that's not the point of learning. But yeah, you should know it as someone who's expecting to take this exam. But in general, yeah. Yeah, cool. Yeah.
In class, we had talked about a formula that was A transpose A B equals A transpose X. What's that?
That's this.
That's the same thing.
That's least squares. It's just instead of X, we call it Y, and then we get B over D. It's arbitrary. Good. All right, other questions?
Can you make like a list of onto and one for
I absolutely can.
synonym for all of them?
And I'll make a nice little drawing for it too, because I do enjoy it. It's a fun little thing. So, onto and one are two of the most important things in this class, and the fact that they tell you a lot about something. You know, one piece that tells you that something's onto or one-to-one, it tells you a lot. These are really good in true or false questions to know the equivalence of things. In my studio, what I usually do is I list a term and we talk about like 8 different ways to define something, and I keep asking until I either can't think of one or get a little tired. So again, all that goes to say, a true or false question usually uses a term that is synonymous with something else. One-to-one and onto come up a lot. Okay, so let's talk about onto first. Okay, onto by definition is having at least one solution for all b. Okay, and this is for the equation ax equals b. Okay, so to have at least one solution, that means we're consistent for everything. Okay, if we're consistent for everything, what can you tell me about my span? The whole everything. Span everything. Okay. Another way to say that, to span everything, is to have your range equal to codomain. Okay. If we span everything, if there's no way to have a pivot in the rightmost column for any solution, we must have a pivot in each row. This is the most typical way that you can tell numerically if something is onto. In each row. Okay. What can you tell me about the number of free variables in something that you know you have a pivot in each row? No.
Equal to n or n minus n.
Give it to me in like a general numerical context. Can you have free variables in something that's onto? Yes. Do you have to? When's the case you don't?
For matrix.
Square. What do we call if it's square and onto? One more step further. One more step further than 1-to-1. Invertible, right? That's what that means. And we'll draw out what the stuff means. Okay. So let's draw out my fun little engineering potatoes. Okay. Okay. So here we have two spaces. Okay. This is where we start, and this is where we stop. We call where we start the domain. Okay. And we call where we end the codomain. All right. We start with where all my x's are. So this whole blob is every possible x I can have. Okay. This blob over here is every possible b I can have. Okay. If matrix A is number of rows by number of columns, how big is the domain? R to the number of. Do we start in number of columns or number of rows? Columns, right? So that is how big this blob is. And this one over here must follow. If the other one's columns, this one must be rows. Okay. What the word onto in general, what does onto mean? Not in linear algebra context. What does it mean to be onto something? Yeah, like on top of, right? So, nothing, no crazy definition here. You know what the word onto means, right? What it means in this context is we can get this space onto all of this space. We can cover everything with what we start with, okay? So, just to describe what this actually is defining, is say we're starting here with all of our x's and we're going through some lens A, okay? So we're going from here into A reflects some way to get to some B, okay? So we have some x, and we go through A reflects us, we go somewhere else. This happens for every single position in X, okay? And the space that we can reach with all of these arrows will be the entire space. These arrows will cover everything, okay? That is what it means to be onto, okay? This colored space we also call the range. The range is just another word for column space. Range is the same thing for the image. Range is what it means is the B's were consistent for. the image that is made onto this blob by going through A. Okay, does that make sense? A lot of words that mean exactly the same thing, right? So this whole thing we call our range, which is always equal to number of pivots, dimensional, okay? And if it's number of pivots dimensional, and it's R to the number of rows, how many pivots do we need to fill the whole space? Number of rows, it's as big as we are. That's why you need a pivot in each row to be onto. Because you need the range, the column space, to be as big as where we're ending up. That's the definition of it. Okay? Make sense so far?
E is a dimension of the matrix.
The D, yeah, I just don't want to write out the word dimensional.
Okay.
Number of pivots dimensional. Okay, it's like 3D, 4D,
So
5D.
the number of linear independent columns.
Number of linearly independent columns, number of columns that are not dependent upon each other, number of pivots you have in the reduced row echelon form of the matrix A, blah, blah, blah. You know these
Yeah.
things. Cool. Any questions on this? This makes sense so far? So the purpose of onto is to be able to get everywhere. What it does not tell you is you could have a second B that goes to the, or a second X that goes to the same B. You could have multiple inputs go to the same output. Okay? Not crazy, that's fine. We just need to make sure we can get everywhere. Okay? So now let's talk about one-to-one. What's really nice is if you can remember one of these, you can remember the other. Okay? This one was at least one solution. So what do you think one-to-one is? At most, one solution for all B. Okay? If onto told us about the span, but it didn't tell us about free variables, what do you think this one's going to do? It's going to tell us about free variables and not explicitly tell us about span. Okay? What one-to-one means is if we have at most one solution, we can never have infinitely many solutions, right? Okay, so that means we have no free variables. Okay, so my null space is equal to what? How big is my null space if I have no free variables? 0. Which point? The origin, the 0, right? Null equals empty, parentheses, point. Okay. If onto is a pivot in each row, what do you think this one is? That's how we find it numerically, right? So now let's draw what it looks like for one-to-one. Let's draw out our domain again. Let's draw out our codomain again. Okay. And here we once again have a matrix A. Okay. So 1, 2, 1. What do we think that at a very high level means? Every input has one output and reverse it. Every output has one input at most. Okay. So that means if we have one, we're 1, 2, 1, right? There's one way to get there if we can get there at all. We don't know if we can span everything, but every X that we put in is going to a unique B. There's no X's that duplicate any, okay? And maybe we don't span everything. Maybe this makes some shape that looks like this. Okay. And we would call that the column space. And we would call it the same thing as the number of pivots. Dimensional. Okay? So what one-to-one means, essentially, is if we take this, we just grab it and we shove it in here. Okay? It has to be big enough to fit. If this is bigger than our codomain, we would have to squish stuff in, and things would have to kind of overlap, right? So what I mean by that is this can be as big as this at most. My domain can never be bigger than my codomain if I'm one-to-one. Okay? Well, what does that actually look like? Well, you can think of it a few different ways. To have a pivot in each column, what sort of shapes of a matrix can I be? Can I be wide if I want to not have a free variable? No, because to be wide means my domain is bigger than my codomain, So this space is bigger than this space, so I have to shove it in there to make it work. Okay? So it cannot be wide, it can be tall, and it can be square. Okay? Over here, we want this one to be at least as big as this one, right? We want to be able to cover everything when we move it there. We can squish stuff over, it can be too big, that's fine. We just want it to cover the whole space, okay? So here, we can be wide, but we can't be tall, and we can also be square, okay? If something is square, okay, and, well, not even if it's square, just speaking of this in a higher context. If we can go everywhere, and we can go everywhere uniquely, what that means is we can trace each b back to an x, okay? The onto part of it tells us that wherever we end up, there's only one way back. And that's what the one-to-one part tells us. What the onto part tells us is we can find each b. There's no b we're inconsistent for. Does that make sense? Tie those two things together, we can call it invertible. Okay, we can get everywhere and we can get back from everywhere. That makes sense, right? Cool. Does that answer your question? Any other questions about onto and one-to-one? And one-to-one. A lot of things here. This is, again, a great place for a true or false. They usually ask some sort of something like this to some extent, even if it doesn't look like it. Okay, it might be there is no b that ax plus b is inconsistent for. That's the definition of onto, right? Then going from there to whatever else the second part of the true or false question is. Yeah.
There is another name for these, do you know, it's like,
Injective and surjective?
yeah.
No.
Okay.
They're just the math terms. Sorry. The math terms are injective and surjective, and if they're both, they're bijective, which is the same word as invertible. It's just,
Okay.
it's words that make you sound smarter, like saying it's a Gaussian opposed to a normal curve. Or saying you're differentiating versus like taking the derivative. It's just the long form of whatever it is in the math concepts. Okay. Yeah.
So if a matrix is both onto and one-to-one, that means it's square.
Well, if it's onto, what are the two shapes it can be?
Be square or be long.
Yeah, square or wide. And if it's one-to-one, what shapes can it be?
Tall and square.
Tall and square. What's the only one that's there for both? Has to be square. Okay, because that means you can fit this space into this space and you're not crowding it. So they have to be the same size. That means everything would have exactly one solution. Yeah,
Does it mean that that's invertible?
that would be the definition of invertibility. Yeah. I really like these drawings. I really like when people explain it like this. Sorry if you haven't seen that before. I think it makes a lot of sense. I'm a very visual person, so I think this really kind of shows off what exactly we're doing when we talk about this stuff. So yeah, transformations. Yeah, we can absolutely talk about transformations. Is there a particular like context or type of transformation or anything like that?
No, it's just been a while.
That's so fair. What was it?
I guess just like if you're given like in order some kind of transformation, like how would you, like you have to flip across this?
Yeah, there's a few different ways to do it. One way that all of you can do it with is to do a CDC inverse. Okay, particularly if you're doing some like you're reflecting over a line, right? You can find whatever you're reflecting. You have one and a negative one eigenspace, right? Because it's a reflection. Okay. You can also find what each of those spaces are just by finding like whatever that line is your one eigenspace, whatever is orthogonal to that line, which is the null space of A transpose, looking at the other part, blah, 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 you can multiply them together. That is a way that will not fail you, but is ahead. Okay. So I think there was a worksheet that described a few transformations. Like some of the ones you'll see will be like transformation of x, y, z is equal to like 3y plus z, x minus z, x plus 10y minus 3z. Is this sort of like the stuff you're talking about? Like when you see it like this or when you see it in like a word form? Both.
Either.
Okay. So this is a form that's meant to trick you. Okay. What this is, if you see this and the question asks, hey, is this a subspace? I can tell you right away that it absolutely is. Because for one, I don't see any plus numbers here, they're all my variables. And what this is actually describing is this is describing the column space. Okay. You've seen it in like the transformation of like blah 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 equals 0 describes a null space. This is how you describe a column space in that manner. Okay. The way we do this is you can think of them as they've basically just given us a bunch of linear equations with variables, right? This isn't anything you're familiar with. So I just make my x, my y, and my z columns. Okay. So for each of my equations, it's going to be a row, right? Each row is an equation. So for my first one, 3y plus z. How many x do I have? How many y do I have? How many z do I have? Okay, next one. How many x do I have? Y? Here.
Oh, my bad.
You're good. 0. Z -1. And the last one, 1, 10, minus 3. They give it to you like this, you can just slap it in the matrix. Okay. A way they could give this would be like, hey, given this, is it onto or 1-to-1? If so, provide a counterexample. Either way. Okay. It's a very common way they'll ask this sort of stuff. And it is actually more difficult than you think. Looking at this, I can go ahead and tell you that this is onto and 1-to-1, because if you row reduce it, you'll get 3 pivots. Okay. So that's how you would be able, I'm not gonna show my work, but trust me. So a way that they would like, I think there was a worksheet that y'all did this, right? It gave you a bunch of matrices, it said if it's not on to provide 2 things, or somewhere you can't reach. If it's not 1-to-1, provide 2 things that get to the same place, right? So I'm just gonna write, I'm gonna do the description of the transformation right after this in terms of words, but I'll show how you can prove it's not onto or not 1-to-1, okay? So not 1-to-1 is easier. Okay, can somebody think of like the easiest case scenario where we can have a of x is equal to a of y? I promise, don't overthink it. Yes, we can solve this equal to 0. And if we're solving this equal to 0, what are we actually solving? We're solving the null space, right? Because if we can find 2 different vectors in our null space, a times x is going to be equal to a times y, right? Definition of a null space. If something's in the null space, a times x is 0, right? Does that kind of make sense? So, not 1-to-1. This is just saying find 2 vectors in null of A. Okay. Not impossible, not hard. You guys know how to do a null space. You've been doing this since like week 4, right? For not onto, bit of a headache, not impossible. What you do is you augment A with like B1, B2, B3, and you treat it like one of those H and K problems. Okay, you're gonna row reduce until you get like a row of zeros in the bottom. So you'll get something that looks like 1, 1, 0, 0, 0, 0, augmented with like 2B1 minus B3 plus, not plus, that was a call, sorry. So you'll get something that looks along these lines. And to not be consistent, just pick a B1 and B3 that make this a non-zero number. So give me an example of a number for B1 and a number for B3 that would make this system inconsistent. And if something's inconsistent, we're not onto, right? So give me an example of a B1 and B3. 2 and 2 gives me 4 minus 2 gives me 0, 0, 0, augmented with 2. Thumbs down, we're inconsistent for something. We've provided that there's something outside of the column space, which we're not. Okay. So I'm going to say this rather plainly. If you're in 3 space and you have one singular plane that you span, what are the odds that you could guess a vector on that plane? This isn't like a numeric question or anything. Like if I have all of 3 space and I have a singular flat infinitely thin plane, what are the odds you guess a vector on that plane? Low, really low, right? So when in doubt, if you're like really stressing out on the exam, just give a random vector. Okay, because there is a really high chance that vector is not on whatever space that you're spanning, right? Because think of it, if we're in 2 dimensions, we only have 1 line, okay? I can pick any vector anywhere up or down here. There's a very low chance that I just randomly pick something on that line, Okay. So this isn't a mathematical way for success, but it is a probabilistic approach to being good. Okay, yeah. So I'm saying this is the correct way to do it, absolutely, where you can get absolute values for what B1 and B3 can't be. B1 can never be twice, B3 can never be twice of B1 ever, right? But if you wanted to just pick random numbers, you're probably right that the vector 1, 2, 3 will be right. Or the vector 8, pi, pi, you know,
Trying to not guess.
because you're trying not to guess on the plane, which is what you used to do.
So, we wanna get credit for-
If it asks for a vector that proves you wrong, it is a vector that proves you wrong. If they say provide a condition for B1 and B3 such that you will not be on the plane, then you have to do this. If they ask for something you're inconsistent for, you can just don't take that too much to heart. This is the way that you can actually do it and be 100% right. But I'm just saying, if you're stressed the fuck out because it's 6 p.m. on a Tuesday and y'all are ready to go home or start your internships, just fucking be done. Yeah,
What do the B1, B2, and B3 correspond to?
just random numbers and some B that we're inconsistent for.
Okay.
They're numbers, yep. It's just saying we augment it with something and we find something that would not be consistent. Yeah,
And back in the one-to-one, in the null space of A, could one of the vectors be the 0 vector?
sure, why not? Yeah,
So for that example,
Hmm.
there's like other B's above. So like 2B minus 3B.
Yes.
Don't care about those.
will they affect how consistent you are? They won't, right? Because they'll be here, they're not changing if you're consistent or not, because we already have a pivot in that row. Okay, so the only one we care about is the one that changed our consistency there. Make sense?
I'm just thinking stuff you're talking about, if it makes something like, is a subspace or not, what are the things that make it fail? Like, I know adding a constant makes it not a subspace.
Yeah, let me talk about transformations a little bit more, and then we'll get into that. Okay, I'll draw some examples that come up a lot, and then we can talk about that. So there are a few examples that you just have to memorize for what transformations are. They are namely projections, reflections, rotations. Okay. What rotations are is you're literally taking your axes and twisting them, right? So do you think you can undo a rotation? So would you call it invertible? Yeah. If you're reflecting over a line, would you call that something you can undo? Would you call it invertible? Yeah. If you're projecting onto a line, would you consider that something you'd be able to undo? No, because you're smashing up a bunch of stuff onto singular points, right? You're getting rid of information. And since you're getting rid of it, you can't undo it, right? So that's why you can kind of think of those things quickly as invertible, uninvertible. Can you undo this? If I'm multiplying all of my x coordinates by 2, can I undo that? Yeah, just divide by 2, right? If I'm adding x and y for my first coordinate and subtracting, and my second coordinate is minus y, can I undo that? Sure, just do the exact opposite of it, right? These are just the kind of ways that you have to think about something being invertible. Okay, that's what it means. To be able to undo something. All right. Okay. So rotations are just something you got to memorize. You guys got to know the unit circle. You guys got to remember what your cosine of 5 pi over 6 is. You gotta, which sucks, but you know, not the end of the world. So that's just a very simple formula where you have for the rotation of a counterclockwise by theta. It's always cosine theta, and this is sine, and this is sine, and this one is negative. Okay. If instead of rotating counterclockwise, we rotate clockwise, what can I just call theta instead and still use this matrix? Call it negative theta, right? 45 degrees clockwise is negative 45 degrees counterclockwise. So I just remember one matrix. Call it done. Okay. Make sense?
Can you also like switch the negative?
You can, because, but if you call it negative theta, right? Then you have cosine of negative theta minus sine of negative theta, positive sine, negative theta, cosine of negative theta. Cosine of positive x is the same thing as cosine of negative x. Boom. Boom. Sine of negative x is equal to negative sine of positive x So that literally just brings the sign out. Okay, so hey, this is my clockwise rotation matrix. Just moving the negative, and that is by the nature of just calling theta negative. It's the same thing. Okay. So the way I like to describe transformation, and the way I think is easiest, is to find the transformation of your unit vectors. Okay, transformation of E1 is equal to your first column. Transformation of E2 is equal to your second column. Okay. So, for instance, if I'm reflecting over y equals x and rotating 45 degrees clockwise and scaling x by 2. Okay. First of all, I would write these as three matrices, A, B, and C. Okay. And I would write this as my input times A times B times C. Right? Because we start with x and we work our way out. We do A first, B second, C third. That's how we do that, right? Opposite order. So I would do this describing my unit vectors, my single length vector in x and my single length vector in y. So if I start with just one x, okay, and then I reflect over x equals y. Well, it tells me I end up here, and now I'm on the top, right? Okay, so now I start on the top here, and I rotate clockwise 45 degrees. That tells me I'm now here. Okay, and now if I scale the x coordinate by 2, I go from being here to now I'm here. Okay, does this graphically make sense of the steps I'm doing? I should draw that pink to keep it consistent. Okay, so what I'm describing is, well, you go from here to here. Okay, so that is the vector. So we're going from 1, 0 to 0, 1 to root 2 over 2, root 2 over 2. And from here, we're going to root 2, root 2 over 2. Right? You can think of it like that, is how we do each of these individual steps. Boom, 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 boom. That's my first column of my transformation matrix. That make sense? Cool. Any questions about how to do something like this? Yeah. So the way we can describe it is by doing it with just a unit vector. We start with 1 in our x, 0 in our y. Okay. And we do each of the steps and we see how things change. We reflect over x equals y, that's switching x and y. Boom, 0, 1. Okay. If now we have the single direction in the y, and we rotate it 45 degrees, it gives me a 45-degree angle with a length of 1, which is here. Okay. So I'm here. The last step was to scale x by 2. So now we're taking this and multiplying our x coordinate by 2. And then we're here at root 2, and then root 2 over 2. Okay. And that's how we take each step to where we want to go. You can also define your matrices A, B, and C, and then multiply them out. Totally fine way to do it as well. How I usually do those is I just kind of think about what's changing. So here, x becomes y, 0, 1, 1, 0. Oh, no. 0, right? What happens to the x vector? It becomes y. What happens to the y vector? It becomes x. And that is my first and second columns here, right? First column describes what happens to x. Second column describes what happens to y. My rotation, not going to fill it in, but it's going to be, well, I am. 1 over root 2, this is going to be 1, 1, this is going to be negative 1, it's going to be positive. Okay. 1 over root 2 is the same as root 2 over 2. That's how we would have our matrix B. And then our matrix C would just be changing x to be 2x and changing y to be 2y. Because remember, you can always read these as just left-right equations, right? So this one is whatever x is, now we have y as my first entry coming out. Whatever my second equation is, now we have x. We have yx, is what happens after we switch. We have a rotated x, rotated y, and here we're going to have 2x and 1y as my output each. Does that make sense? It's like the single steps of how we're getting it. Yeah.
How could you reflect this with like y equals 4x? Because like
You can.
Yeah, but like how would you do the matrix?
I would construct the CVC inverse matrix. You know your eigenvalues, reflection, 1 and negative 1. Okay. So, something that a lot of you probably don't remember from algebra. If we have a line with slope m, how do I find a line that's orthogonal to this?
It's the.
Almost. The negative reciprocal, okay? You will always be able to find a line that sticks exactly off with a slope of -1 over m, okay? So for example, you said y equals 4x, right? What I would do is I would make a C in the D. We have C. Well, I'll do D first. Okay, D is my diagonal matrix. It's a reflection, so we have 1 and 0. My one eigenspace is the thing that's on the line, the thing that's not changing as we reflect over. So what is some vector on the line y equals 4x? Give me a point. Almost. What is my x? 1/4, right? X is 1, y is 4. Okay. Couple ways you can do the second one. You can think of this as y equals -1/4 x. Or you can just take this vector, switch it, and make one negative. You'll get the same answer. Okay. So here you'll get -4, +1. And hey, you have a C and a D. You can do a CDC inverse and get your generalized matrix A that describes the transformation. Sucks, not impossible, right? Questions about that? That's about as hard as these things get. It's multiplying 3 2x2 matrices. You guys have 2 hours and 50 minutes on this final for 10 questions. It's like 20 minutes a question, and some of them are just true or false, right? Some of them are going to be least squares, which you can do in a few minutes if you practice on how to do it, right? As a note, I usually take the exams when I proctor, but I haven't been able to proctor any of the exams this semester. The final usually takes me about 15 minutes, which means it should take you probably about an hour and 15 minutes. So when you like make an exam and describe this sort of stuff, right? The person who is creating it and the person who like really knows the material should be able to do it very quickly, right? I know this stuff. I took this class in 2017 when I was in high school. I've been teaching it for a lot of semesters, right? So this is something I know very well how to do. It should take you all about 5 times what it takes your professor to do an exam. If a professor ever tells you, hey, you have an hour and 15 minutes to take this exam, and it took me an hour, what the fuck? That is not good. That is not how people should strive to write these sorts of things. So all that goes to say is this is never meant, like people don't press time for this exam. Okay, that rarely happens. So just take your time, take some deep breaths. It's never going to be anything crazy. If you want to work things out the long way, you have time to. Okay, if you want to check yourself, please do. Right? You have the ability to do this, and you have the time and resources to do those things. Okay. Other questions? Yeah.
Where did you get the D inverse from? Where did you get the D from?
Since I know that this is a reflection, what are my eigenvalues?
Okay. Fine.
Yeah. So these are arbitrary. I can switch them, right? But then I have to switch these columns because they have to line up. Okay. Yeah.
Okay, back on the matrix for the B transformation.
Mhm.
Wouldn't the bottom?
No, it's clockwise.
Make-
Yeah.
I was just confused. Okay, that's kind of complex.
So fun fact about school in general, the little things like computation won't count as much against you as if you can actually do the whole thing, right? You have a 10-point problem and you miss a negative on an eigenvalue stuff, finding the null space, you're not going to get a 0. Probably going to get like a 9. Okay. One of the pieces of advice I got when I was first started teaching was never do arithmetic in front of anyone ever, or you will get it wrong. So I apologize, but it happens, right?
I just want to make.
Yeah,
sure
you're
I
right.
was
No, you're so right.
understanding.
For correctness, this is absolutely
Okay.
right. Okay. Other questions? Big picture, small picture, specific, what works, exam stuff. Yeah.
What is stuff that makes it fail in subspace?
Oh, yeah, subspaces. Yep, let's go back to this. Okay, subspaces have 3 requirements like we've discussed. Okay. Rule number 1 is contain 0. Rule number 2 is closed under addition. And the other is closed under multiplication by some number. Okay. 3 things that define a subspace, and they define linearity as well. Some operators you all are much more familiar with that are closed under linear stuff is like derivatives, integrals. These are how you get those rules. Your product rule, well, not your product rule. You're like, you can distribute like an integral if you have the addition of 2 different things, right? That's where this comes from, because they're linear operators. Multiplication gets tricky, and especially like f of g of x, not used properly. But these are where we get that sort of stuff. So, there are a lot of different ways to explain each of these three qualities. I'm going to describe them graphically first, and then I'll talk about how to do them algebraically. Okay. So they'll always give you some sort of starting place. Okay. And one of the things I'll note is that whatever they give you is the form of a column space, a null space, an eigenspace. Boom, you're done. It's a subspace. That's why we talk about them in the first place for this class. Column space, a null space, and a subspace are, by definition, subspaces. Okay. So if they say t of x, y, z is defined as 3x plus 4z. I got this out of order, but who cares? Plus 2y is equal to 0. How else can you define this? Well, we can define it as 3, 2, 4. I know I got it backwards, and I'm very sorry. We can define something that looks like this, right? Solving for solutions to a homogeneous system, and what do we call that? Null. Okay, this is a null space. Is it a subspace? Cool. No more thought required. Right? If we're solving an inhomogeneous system where this is 2 and this is 2, what kind of space is this? Nope. It's just a solution set to an inhomogeneous system. Okay. So like when we solved these sorts of things before, we get like x vector equals like x3, 2, 1, 1 plus like 4, 2, 0, right? And when we would graph the null space would always, and that starts the origin, go from the origin and make a line, right? What would an inhomogeneous solution look like with respect to this line? It would be exactly shifted in some way, right? By what we call the particular solution, b sub p, which is this vector, okay? What do you notice about this line? What does it not touch? Okay, we don't touch the origin, it would be a subspace. No more thought required. Rule of thumb, if you see like hanging out constants, you're equals to 1, you're plus 6. Not such thing. Right.
Oh, because you move it to the other side.
Same thing. Okay, so that's some quick tricks for what you'll probably see. Some things you run into frequently. X times y is equal to 0. Okay. If we were to graph this, what would this look like? It would look just like our axes, right? Because either x is 0 or y is 0, or they're both 0, right? So this is what my space would look like. Okay. Graphically, to be closed under addition means I can take any two vectors on these in the pink space, add them together, and I'm still in the pink space. Is that true here?
No.
No. Why?
Get off.
Yeah, we can add something that points this way to something that points this way and get over here, right? That's when we're not closed under addition, when we can add things together that removes us from our space. That's what that means, okay? On the same note, for something to be closed under multiplication, okay? If I have any vector in this pink space, and I multiply it, is that? What is
It's like those.
Yeah, I don't know.
Oh, that's just so gross. I'm so sorry. Styles. Here, if we have any vector on this pink space and we multiply it by any number, do we stay in the pink space?
Yes.
Right. So this would be closed under multiplication. Does this contain the origin? Pretty clearly, yes, right? This is how I like to look things very quickly, right? Oh, I plot it. Oh, that doesn't look like it should. Moving on. Okay. Another classic example would be x, y greater than equal to 0. What is this equivalent to saying?
They're both negative or they're both positive?
They have the same sign, right? Which quadrants am I in on a coordinate plane?
1 and 3.
Yeah, over here and over here, right? So now I'm going to make that my space. Does that include the axes?
Yeah.
Yeah, because we're equal to 0, right? So I'll draw it as here, this whole thing, here, this whole thing. Okay? So, looking at this one, could we take two vectors and get out of this space?
Oh, yeah.
It's all good. Yes, right? We get out a vector that points this way and a vector that points this way, get over here. Same sort of thing as the last question, right? The closed or multiplication, this is,
Yes.
think of anywhere you can start in this space. Is there any number that you can multiply by to get you over here or over here? Not a real number. At least in rectangular coordinates. But no, this would be closed or multiplication as well. Okay. What about if we have x and y, x comma y are greater than or equal to 0? Which means I'm only in the first quadrant. Okay. Now, if I'm in the first quadrant, are there any two vectors I can add to get me out of the first quadrant?
Real version.
No. You can add. Can we add any two things together to get me out of the first quadrant? Yes or no? No. There's no way I can get in this direction or this direction because I don't have any pieces that point in that direction. So we always have to start at the origin, right? So this is something that I would call closed under addition. Does this contain 0? Yeah, we have two conditions met. Is this closed under multiplication? No, why? Yeah, multiply by a negative number, right? If I have some vector in the space and I multiply it by -1/2, boom, out of the space, fails, closed under multiplication. Does that make sense? Yeah. This is how I like to do it. I like graphing. I think it makes a lot more sense to look at it and tell if it's a subspace. Algebra can get a little complicated. Okay. If we wanted to look at it from an algebraic perspective, okay, let's start once again with x, y is equal to 0. Okay. To check if the 0 is contained, that's pretty easy, right? Plug in 0, see if it's true. Cool. All right. Now, let's pick two vectors that satisfy this, okay? Call them x1, y1, and x2, y2. Sometimes you'll see this as u1, u2, and then v1, v2. It's the same thing. We're just picking two vectors that make this true, okay? So what has to be true about x1 and y1? What has to be true? At least one of them has to be here properly, right? What about this one? Same thing. At least one of this one, at least one here has to also be 0, okay? So the question is, if I add them together, must one of them still be 0? Why?
X and 1.
Yeah, think like if I pick opposite cases. In this one, if I pick x1 to be 0. In this one, I pick y2 to be 0. When I add them together, well, this is 0 and this is 0. But those two other numbers have to be 0? They have to be. We could work this out properly, okay? And we'll get x1 plus x2, y1 plus y2 is equal to 0. Okay, we're gonna FOIL this out. x1, y1 plus x1, y2 plus x2, y1 plus x2, y2 is equal to 0. Which of these things do we know stuff about? Yeah, we know stuff about this one. This is 0. We know stuff about this one. This is 0 as well. Okay. Is there any guarantee that these two middle ones are 0? No. So that's why this would fail being closed under addition. Because we can't guarantee that these numbers are 0. We can guarantee that these are 0 by the pre-existing condition, but these two don't have to be 0. They could be if x1, x2, y1, y2 are all 0s. That would satisfy the condition. But... Okay, so that's closed under addition. Closed under multiplication, what that would look like is we pick like c times x and c times y and see if it's true. Okay, so this gives me, if we plug in my x and y to x times y equals 0, cx times cy equals 0, c squared xy is equal to 0. And what is x times y equal to? What did we start with? Those are 0. So with c squared, I'm going to change that. Is there any c I could pick such that c squared times 0 is not equal to 0? No. So that's why this is closer to multiplication. C can't make this false. But up here, our choices could make that false. That's the difference. That's the algebraic computation. That is a headache.
So you kind of have to just try a little bit here, or like test it till it doesn't work.
You have to think about it in a broad context and what might be the exceptions. Okay, these are about as complicated as these examples we get. Sometimes you get like an absolute value. Nothing insane. Probably not linear. Not a subspace, but you have to figure out if it's not closing or addition or multiplication. Okay. Like some of those are like the absolute value of x plus y is equal to whatever, right? And then you just go. Cool. Any other questions about any of this? Okay. What other questions do we have? Yeah. Sure. Do you have a specific problem? Okay.
Sorry.
No, that's fine. So I'll just kind of talk about generally how to do it. Okay. Diagonalization. Diagonalization is one of those things that I don't love the term diagonalization because it doesn't tell you much about what we're actually doing. Diagonalization is properly called eigendecomposition. It's taking a matrix A and breaking it up into parts based on eigenvalues and eigenvectors. Okay. To me, that makes more sense for what we're actually computing, right? So all diagonalization is finding eigenvalues and finding eigenvectors. Okay. So to find eigenvalues and eigenvectors, you'll always do the exact same process. Determinant of A minus lambda I equals 0, and solve this and you get your lambdas. Okay. Null of A minus lambda I for each lambda, solve this, you get your eigenvectors. Okay. Cool. So to be diagonalizable, you must be able to fill in two matrices, C and a D, such that some matrix A is equal to C, D, C inverse. Okay. On an exam, if they ask you for the define a matrix C and D, describe a matrix A is equal to C times D times C inverse, you just need to find C and D. You won't be expected to also provide C inverse. It's kind of arbitrary. There's nothing interesting about us asking you to find an inverse of a matrix. Okay. Matrix D is always the first thing you do. It is a diagonal matrix where you put all of your lambdas on one diagonal. You'll always have lambda to the n. Okay. So solving the determinant of A minus lambda I, you'll always get lambda minus lambda 1. I'll call this a cubed. Lambda minus lambda 2. Maybe this one's 6. And then lambda minus lambda 3. Maybe this one's just squared. Okay. Looking at this here. Okay. One of the things a lot of people also get mixed up is the difference between algebraic and geometric multiplicity. Okay. What is algebra? Solving for an unknown variable, right? The general study of numbers you don't know. Numbers. Is an eigenvalue a number or an eigenvector a number? The eigenvalue is a number. Okay, what is geometry? Study of shapes, right? Okay, is your vector a shape or is your eigenvalue a shape? Your vector. Your vectors have geometric multiplicity. Your values have algebraic multiplicity. Okay, that's how that works. That makes sense? That's how we keep those separate. Algebraic multiplicity comes from equations like this, where we're solving for the zeros of something. The algebraic multiplicity is how many times it pops up when we factor it out. Okay. So while looking at this matrix, okay, let me give you actual numbers here. Call this 8, call this pi, let's call this E. Okay, E being 2.7, whatever, not just a letter. So first and foremost, is this matrix invertible?
Yes, yeah.
Why?
Have a 0 eigenvalue.
There's no eigenvalue that is 0. Okay. If we are invertible, what do we not have? Broader, not with eigenvalues. We're invertible, what are we lacking for a matrix A? Free variables. If we're lacking free variables, how big is our null space? Right, just the point, the origin, 0. Okay. What is another word for a null space? The 0 eigenspace, right? We define an eigenspace as the null space of A minus lambda I, okay? If lambda is 0, we're finding the null space of A minus 0I, or just the null space of A. That's why sometimes to confuse you, they may say the 0 eigenspace has a dimension of 3, okay? What is the dimension of the column space? Well, you do rank nullity theorem, if you're 8-dimensional, your 0 eigenspace has a dimension of 3, it tells you have 3 free variables. Okay, you can go from there. Right? What is my algebraic multiplicity of 8? 3. What is my algebraic multiplicity of pi? 6. What is my algebraic multiplicity of e? 2. What is the sum of my algebraic multiplicities? 11. Okay, how big is the original matrix A? It must be 11 by 11. Your algebraic multiplicities, to sanity check yourself, should always add to n. Okay? If you have a 3 by 3 matrix, you're gonna have 3 eigenvalues. You're not gonna have 3 different eigenvalues necessarily, but there will be 3 with some either repetition or not. Okay. So going from here, what diagonalization is this algebraic multiplicity is equal to geometric multiplicity for each of your eigenspaces. Okay, so to be diagonalizable, how big to be diagonalizable, what do we want the dimension of the eigenspace of pi to be? To be diagonalizable, it must be 6. That doesn't check off all the boxes, because what does the dimension of our 8 eigenspace have to be? 3. And what does the dimension of our E eigenspace have to be? If any one of those fails, are we diagonalizable? No. There's another little trick here. If my algebraic multiplicity is 1, okay, and I have an eigenspace, what is the smallest an eigenspace can be? The dimension of 1, a line, right? That's the smallest space we can have. That's interesting. So if we have an algebraic multiplicity of 1, what must our geometric multiplicity be? 1. In general, our geometric multiplicity must always be at least 1, and at most our algebraic multiplicity. Okay? So I'll write that as 1 is always less than or equal to geometric mult. Always less than or equal to algebraic mult. Okay? If these two are equal for all lambda, we call this diagonalizable. Okay. So far, so good. So another way you can see this is if like we're filling in a matrix, right? These my eigenvalues. That's not hard. We'll call it like 8, 8, 8, 8, pi, blah, blah, blah. You know, whatever. Okay. Your C has to be able to fill this with vectors as many times as you have eigenvalues, right? This is going to be 11 by 11, so this is going to be 11 by 11. Okay. We have to have 3 vectors to fill in my 8 space, right? So we have to be able to fill that the same number as we have eigenvalues, okay? That's why our algebraic and geometric multiplicities have to be equal to be diagonalizable. We want as many vectors as these each pop up, right? So we want that to be able to happen, and if we can't fill C, then we're not diagonalizable. Diagonalization is just filling up C. That's all it is. And if you can do it, you're diagonalizable. Okay. Some shortcuts are like, hey, I have an 8 by 8 matrix that has 8 distinct different eigenvalues. Am I diagonalizable? Why? What is my algebraic multiplicity of each of those eigenvalues? 1. So by definition, what is their geometric multiplicity? Also 1, right? Non-zero, 1. Okay, so that's how you kind of make that one. One other thing I'll say about this What is my determinant? I don't want the exact number. Okay, it's not 0. I want a little bit more specific of a case. You don't have to work it out, but what is it going to be equal to?
8 cubed
8 cubed times
pi to the 6th.
pi to the 6th times e squared. So I have a 2 by 2 matrix. My determinant is 16. One of my eigenvalues is -8. What is my other eigenvalue? -2. Is that matrix diagonalizable? Why? 2 distinct eigenvalues for a 2 by 2 automatically tells me I'm diagonalizable, right? It's like the chain of events of how you think about stuff like this. It's a great kind of true or false question. My determinant is this. This is one of my eigenvalues. Okay, you don't even need to find what the other one is. You know that it has to multiply to be, or you can just look at the determinant and be done. Okay. Yes. So if I have a 2 by 2 matrix, my determinant is 16, and one of my eigenvalues is 6. No, not 6. That's too hard. 9. No. 4. What is my other eigenvalue? 4. Do I know if I'm diagonalizable? Why? What is my algebraic multiplicity of lambda equals 4? 2. How big do we want the geometric multiplicity to be? Is it? We don't know. Could be. You need more information than that to get there. Make sense? Another type of problem they may ask. They give you a 5 by 5 matrix. Okay. They give you 4 different eigenvalues. Say your eigenvalues are 1, 2, 3, and 4. 4. 1, 2, 3, and 4. Okay. They say that lambda equals 4 has an algebraic multiplicity of 2. What would you do to find out if this matrix is diagonalized? The only thing you need to look at is A minus 4i. Why don't we need to look at the rest of them? Because their algebraic multiplicity is 1. So what must also all of their geometric multiplicities be? Okay, but for lambda equals 4, we had an algebraic multiplicity of 2. So what must its geometric multiplicity be? To be diagonalizable, 2, but we don't know that. That's the only thing we have to check there. Okay. Kind of like a sanity check. Like, oh, it's a 5 by 5. I only have to do one little null space here. You don't even have to do the full null space. You're just looking for free variables in that matrix. Okay. Any other parting questions? Yeah. Yeah. All you're checking is this. Is geometric equal to algebraic? Geometric is the dimension of your eigenspace. Dimension null a minus lambda I. If that number is equal to this number for all your lambdas, 2 thumbs up. Okay. Anything else? Good luck on your final. For those of you in section A, I will see you next week. I am around. Why is this always so difficult? Stop.